Hi and welcome to this tutorial. Today we're doing some kind of spinning confetti kind of thing, something like this. It's basically a pop sim which has air resistance and a kind of swirly motion when things get moved in a certain direction, etc. etc. It's very basic in some degrees and a bit advanced in others. It's quite fun. It simulates in real time pretty much, and yeah, it can be used for various kind of things. I did this for one project and then reused it for others, and yeah, I just want to show you guys. It basically is driven by orientation and rotation, and that's pretty much it. So yeah, let's get to it. So we start up by download a GeoNode, which I already have. I went ahead and did that. Sorry, I started recording this and then I realized I had projects up that was very NDA'd. So yeah, I had to stop the recording and redo it. And there I had already created a GeoNode. So you have to do this on your own, and then after you've done that, you can drop down a box. We make the box 10 by 10 and we move it up like 8, and this will be our emitter. There it is. Cool. We want to emit inside it, so we drop down an ISO offset, and then we drop down a scatter, and we take it down to like 1 point right now, because we're just gonna do this as easy and fast as we can. And after we've done that, we're just gonna give this little dude an attribute randomize, and we're gonna randomize the orient, because the orient is what drives it, like I talked about earlier. And that's 4 dimensions, and it goes from -1 to +1, and it's normalized. It doesn't matter, but we're also gonna create a scene marker for orient, because that will be needed. We will do a few of these, yes, because it's vital to have that kind of thing. So we have an orient here. That's good. And we could just do like this and see we have different orients. Good. And then we're gonna drop down an attribute triangle. We're gonna call this spin. And what we're doing here is basically we're creating the spin axis, and that is a vector. So we just do vector spin axis, and that should be equal to randomness of the pt num plus a number plus the $f, because we're gonna scatter things each frame here. And then we have to, now we get a value from 0 to 1, and we want that to be from -1 to +1. So we're just gonna do at spin axis. We could keep the v here, you don't need it, but it's kind of nice to have that praxis thing going on. Praxis, funny word. So we just subtract -0.5, -0.5, and -0.5. That's good. And I'm just gonna save as well. And hopefully I can do this in a good way. Sorry, I'm just gonna do a tutorial. Let's do a new folder 3, because this is my, actually I have a second tutorial that I haven't shown yet. So we call this 1, 2, 2, 1. So good. So the spin axis is moved, and then we can just, sorry, that wasn't meant. We can just normalize it. V at spin axis equals to normalize at V at spin axis, and that's good. Good. And then we do a spin amplitude, which also is random, and that equals to random at pt num plus $f plus and we then just multiply that by a float spin amp. So we have a general control over it as well. So that's good. We have it now, and we can build a visualizer for it. It's always good to do for this kind of thing, because it will be a lot of sorry, spin axis. That should be spin. Spin axis is what we want to show. We don't need a spin amplitude. That we can just look at. So we call it spin axis, and the value should be spin axis, and not capital A, but small a, and we visualize that as a vector. Good. We have a spin axis, and if we do not look at the orient, we can see we have a spin axis. And if we bring up a lot of more points, they have the same spin axis. Why is that? Okay, so forgot something here. Is plus equals to, so good. It just normalized the thing, so that was fucked up. Sorry. And now if we look at spin axis, it's random. That's good, and we can bring down the scatter to 1 again. Good, sorry. Always small things you forget. So that's good. We have the spin axis. Yeah, we're gonna bring down this as well, so we get spin amplitude set to 1 at the moment, and then we just do. We're also gonna create a point rest, and we don't just call it rest because we call it point rest because we will have another rest as well for the other geometry. Not sure if you use it, but if you want to do procedural shading, it could be good to have a rest position as well. After that, we bring down the popnet, which is where the main things happen. And here I'm gonna explain a little bit. So sorry, I'm just gonna do a new one here. Yeah, so basically what we're doing is we have these points, and they have their axis, which looks like this pretty much. And what we then do is we have geometry that looks like this, or something that we copy onto them. And the thing is, like, this axis, the y-axis, is always pointing upwards, so it's always the long side here, and that we can use a lot. So pretty much what we're going to do is when these are facing upwards, so this is up or this is down, either thing, then it's going to be pushed on the opposite force of gravity. So gravity is pulling it down, so we're going to push it a little bit up with another force, and we're also going to push it to the side, and that side is determined from the rotation. So that's pretty much the idea. So what we do is we compare this vector, the y vector here, and we compare that to just we have two versions of doing this, and it gets a little different result, and both are cool and good, but different. So the first option is just compare it with a straight vector pointing up or down, and then calculate the dot product from it. So if they're both pointing up, we know that we have something that's perpendicular to the kind of ground plane and gets, or to the straight down vector. So we just calculate the dot product from those, and that gives us a result from -1 to +1, and then we can use the absolute value of that. Yeah, and it tells us in what direction the plane is lying in. So that's kind of basic. The other option is to compare it to velocity, and that gives us a little bit different result, but it's pretty much the same because the velocity is mostly downwards, but it's tend to push a little bit to the side as well. And in those cases we get like air resistance when it's flying to the side as well, like that. Super nice. I'm so good at drawing. So that's the two options we have. But we're gonna start up with just the down vector. And yeah, and besides from the push upwards, we will also get another thing, and that is the side push. So basically what we're saying is that when it comes like this, kind of, we say that here's the thing, and it's fucking, I'm drawing with the mouse here, and it's spinning like that kind of direction. We want it to push that way, and the way we're doing that is we take this and then we compare it to, so then we have this up vector here, and we compare it to the last frame, and the last frame maybe the up vector was here, and then we subtract these vectors from one another and we get a new vector that's pointing this direction. And that's good, because that vector then can be used in order to calculate, if we take that vector and we use this original vector and we do a cross product from them, we get something pointing towards us right now. And then if we take that and we do another cross product, we get something that points in that direction. So that's good. It tells us in what direction it's spinning, and we can use it to push it in that direction. And that's kind of what drives it. You can see it if we look at this. You can see that, like, see, it's kind of, I don't know if you see it, but it's kind of, yeah, let's look at this little fucker here. When it comes down, you see that it turns up and it's pushed out to the side, and that's because of that effect. And it's like what drive everything, so it's, you see, it's pretty much on every one of them. But it's gets, yeah, you see it there as well. So that's what gives it its look, pretty much. But we'll get to that later. Let's start with the push up thing. So, or let's actually start with gravity, because that will be needed. So start with a gravity force, and we're also gonna drop down our merge here to merge everything we need together. And let's also put down a pop drag. We will do our own drag pretty much, but we kind of can use a regular drag as well. Let's bring it up to like 10, just to be able to watch this. Sorry, we're gonna source, we're gonna all points, yeah. And now we're back at having the spin axis to be fucked. Why is that now? Okay, fuck it. Let's just move on. We're not doing 1 point, so it doesn't matter. And if you're doing that, you have to use position or something as well. So that's fine. I just lost a little focus here. So yeah, we have a pop drag, and the main thing is the spinning thing. So we kind of remove this because it annoys me. We're just going to put on the orient. And yeah, let's pop down a pop torque, because that's what gives us the spin. And we can have it after the drag, it's fine. So basically what we're doing here is we're using an expression, and it's very basic. We just say that the axis, we can do, the thing is like to do is just do a pass through so you get all the variables here. So axis should be equal to v at spin axis, and amount should be equal to, what's it called? Good thing that even if it breaks, it's called, let me see here, what do we call it? We call it spin amp, I think. Spin amp, yeah. Amount equals to at spin amp, and we need that there as well. So there we go. That's good. And we're also gonna bring in a noise here to make it a little bit different. So we're going to do a vector which we call noise, and that's equal to x noise, which is a function that gives us noise from the position. So do v at p multiply by channel vector, which should be like frequency, and then we can just multiply that by channel v. Yeah, we could do float, but fuck it, let's do channel v amplitude or noise amp. We can't use channels that already exist. And then we just do axis plus equals to noise, so we do it additive. I think that's fine, and we can bring this up, and we give it a little bit of yeah, so that's good. And if we look at the torque here, maybe yeah, it does change. You see, we get a little bit different here. So we could visualize that as well in order to see how much effect this has. But you keep it at something like 1 and 0.4, I guess, maybe. I'm not sure. Maybe we need to bring it up more, but yeah. Let's do it like this. And what we get now are spinning things. And here's the thing, since this is annoying to me, I'm gonna fix this now, sorry. So spin axis, we can't do, we do fucking, instead of random, we just do x noise here as well. At p, good. Let's see that the spin thing here is different, cool. That's what I wanted. Good, and yeah. And also one thing we're gonna do here is global seed for attribute randomize, also gonna be $f, so we get that random as well. So now if we look at this, we should have different those, and they are spinning in different ways, which is cool. They're spinning super fast. We will drag this as well, and you see they have a random different amplitudes, etc., which is good. So the pop torque is done, which is one of the big things here. We have a pop drag, and we could pop down a pop drag spin as well. So just let spin resistance like 1. I don't know if that's good. Gives us a little bit. So they're not just continue to accelerate forever, which is good. Great. Now we move into the a little bit more technical stuff. We're going to do this in pop VOPs. I did this in Vex Wrangles before, but it's easy to understand here, and it's not that complex. So I think like doing it this way is easier and not that hard to understand. So what we're going to do now is we're going to bring in our axis, which is the green axis here. And in order to visualize this, it might be good to do like a copy to points down here. I'm just going to bring that in, and we're going to do a little bit of a box, and we can exaggerate the size here, maybe not 1 by 1 because that's too much, but we do like 0.1 there maybe. Yeah, so that's, there you go. And as you can see, the green axis is what tells us, since we do it 0.0 in that axis. So that's good. We have these and they're falling like they should. And they're too big now, so never mind that, but it's easy to visualize like that. So what we're going to bring in is this green axis, as you can see. And that's pretty straightforward. We just bind in the orient. And we use orient here. Oh, not capital letters. Orient. And we bring in as 4, no, not matrix, sorry. Where is it? 4 vectors, 4 floats, vector 4. There it is, not 4 vectors, sorry. And we convert that quaternion to matrix free, which is the free axis in a matrix. And then we do a matrix to vector. Matrix free to vector. And that's good. Here we have our axis. If we plug it into like the normal, and we put that down, and we see that we have a normal that is facing in our green direction, as you see as we turn it on off. So that's super good. This is all we need for pretty much everything. Then we do the constant now. We do not compare it to the velocity. We're going to compare it to a constant, which is just a straight up vector thing. And yeah, we can just take the dot product from these. So we take the second matrix row, and we take that, and we get a dot product, and we can bind that as, export that as dot. So we have dot product exported, which is good. But right now we're going to use the absolute value of the dot instead. So let's do that. Let's take absolute, and what we could do here is we could, in order to visualize this, we could plug it into CD. And let's move back and let's look at the copy to points. As you see, when they get turned down, they get the white. They get white, and when they get it straight up, they get black. So that's good. We know that when they're white, we want to apply our forces, and when they're black, we want to remove them. Oh no, that's too... So there, is this correct? Yeah, it seems correct, right? Let's just remove the shading, because it's hard to tell with the shading on. Yeah, they turned. Yeah, that's good. It's always consistent because I think like it's very. They look white for a long time, and that's just how it looks, you know, when you have a linear value of it. So that's good. It works. So we know now that when they have a value of the absolute value here is 1, we should give them air resistance. So the air resistance thing should come from the velocity. And that's important actually. So what we do is we just pretty much can take the length of the velocity, and we can then just multiply that with a constant. I don't know what value. Let's put down high value just to show things here. I don't know. And then we can do a vector set component, and we're going to do this as a second component. I'm going to use this, so that gives us an y value, and then we could pretty much just add this to our force, which brings in there, and Let's plug that into the force. Good. Now we should have something that gives us... Maybe we should exaggerate it more actually, because it's kind of hard to tell right now. So let's just, in order to, one thing, let's just lock it here, remove so we don't show normals, and we just see here, just see that everything is right. We have the velocity, we have a multiply constant, let's bring it up to 2000, and just see, yeah, so okay, that's, bring it down to 200. We want something that's visual, but okay, it's just, okay, one thing we forgot here is we forgot to multiply this, sorry. So here's a problem. Before we add it to the force, we should of course multiply it with the dot product. That's like the whole thing here, and I just forgot about it. So we do that. And now we shall see that, yeah, they're falling and they're getting up, and yeah, compared to... So it's super strong. If we just take it down to 20 again, I think we should be able to see it, but it... Yeah, it is there, but it's kind of hard to tell. But we bring it up to 50 maybe. We have something that's not look extremely exaggerated, but still. Yeah, you can see that they... Yeah, now you see it clearly. They're so big, so you need to exaggerate here, but I think 20 is something that we want to aim at rather in the end. Good. And what I also want to do here is I just want to bring in noise. So let's do that. Let's just take the position and bring in an AA noise and do a fit range of that from minus 0.5 to 0.5, because we maybe do like 0.3 to 1, sorry. And then we just multiply it instead. I thought to do it additive, but we do it multiplicative. So we get some, depending on where they are, they kind of get less and more, just so it's a little bit random. It's hard to tell now. It will be clear when you see it in... I mean, just layering things, adding a little bit of complexity. It's hard to tell when you see it like this, but it will be obvious later on. So cool. We could also, in order to visualize this a little bit, we can plug in the absolute thing to the CDSN, so we see like the white ones get a little upwards movement, and then they get a little faster movement. And this will be, of course, be clearer if we bring this down a little bit, I guess. So let's just bring this down. We can bring this down to like we can really small, and bring this down to like 0.3, and 0.3 is maybe keep it like 0.5 there, so they get a little bit of length. Yeah, you can see that they have a movement that is, yeah, you see like that one that's just not getting the straight white gets a faster movement. So that's cool. It's not that obvious right now, but it's especially since we have the other drag force as well. They get dragged a lot either way. Yeah, so that's pretty much it for the push upward thing. So let's move to the push side thing. We should call this push up. Why do you give me error, and why are you capital letters? You shouldn't be capital letters. Push up. And yeah, so do it on another pop-up, and let's call this push sides. We could do this in one as well, but I think it's a little bit easier when we do it like this. So the push side things, here it gets a little bit more complex. It's not super complex, but like I talked before here, is what we're going to look at now is the spin. So we have our points, and we have our up axis, and we look at this for the previous frame, and then we look at this for this frame. We calculate this vector here, which is just like the yeah, you just subtract them from each other pretty much. And then from that vector we look, then we have that vector, and then we have this vector, which is our original upwards vector thing. Or it's actually not like that, it's rather like this. It's kind of hard to do in 2D, it's kind of hard to draw for me. And from those two we can, as you see now, we have actually we draw this from like 0 angle. So from the, if we just put them at 0, a Cartesian scale, it's like a vector pointing that way, and then we have vector more or less pointing like that. And from those we can take the cross product, which basically just gives us, I don't know if you know the cross product, but it's basically gives us a plane. So when we take the cross product, we can see these things here as a plane. So we see this as a plane, and then it pretty much gives us the normal from the plane, so to speak. So it gives us something pointing straight at us. And then we reuse that and do another cross product with this thing, and that gets us to pointing forward direction. I will show you now instead. So we can go back here and we can take this and we can just copy this thing because we need to do that. And sorry, before that we're gonna do something pre-solve here, and that is just to store down the orient from the previous frame. So we call p at old orient equals to p at orient, and p is for vector 4 quaternion. So old orient, we call that. Good. And now we can bring in this thing. So we bind in the orient, and we also bind in, call this old orient. That's good. Now we have both of them. Then we can do, I want the old because it's older on top, right? Old one on top, maybe not. We just subtract here, not subnet, we do a subtract. So what you do then is that we take the second one from this one, and we take the second one from this one, and we get a subtracted. We get the distance between them, so to speak. We normalize that, and we take this one, and we do the cross product, and we do the cross product from that one. And it's already normalized, so you don't really need to care about that. And then we basically take another cross product, and it doesn't really matter which one we do this from, but I think we should do this from that one. And we take this cross product, and here we have the pointy thingy. We could bind this to just show it. We call this side push or something like that, and that should be a vector. And let's just visualize it. Side push, and we call it side push, and we visualize this as a vector. We close it and we play, and yeah, it's let's just remove the axis. Okay, so here's the side push. It's kind of hard to tell, but it's rotating, which is good because the thing is rotating. And this will of course then be let's see if we can do it like this. Yeah, you can see it's pushing in. Yeah, it's following the rotation, and it's not very obvious when you see this thing, but the thing is like it's negative right now. We should have it on the other way. So the thing we're gonna do is just, you could probably just switch around these cross product things. I guess if you do other way, it will be correct. Maybe if you do it like this and this instead. No, sorry, that instead. Is that the other way around? Let's just see. I'm not sure. Fuck it, we go back to the way it was and we just negate it because I know that that will be correct because that's what I did last time. So let's do it like that. And let's just negate it. Good. And yeah, we need a multiply constant here as well. Let's do, I don't know, clear this up a little bit. And this multiply constant will then, this gets a little bit messy, but let's try to keep it tidy. Can we? No, fuck me, that wasn't a good idea because that gives us that. Yeah, so what we want here as well is the dot product. So we're gonna bind in that because we just want this to, you know, be a applied when the dot product is correct. So we bind in the dot product. The thing is here as the dot product. Let's see that we did store the dot product, right? Yes, we did store the dot product. Good. Sorry, we're in the wrong place now. Yes, and what we want to do here is we want to do two fits. We want to fit this from -1 to 1, and then we're going to fit it back from -1 to 1. And the reason we're doing this is because we can do a ramp in between if we want to art direct this. So we do a ramp parameter. I don't think we're going to do that much with it right now, but it's called dot ramp. Because it's good to have if we want to you know, change where it's applied or not. So we can take this multiply constant and we can multiply this in turns with our dot product over our fixed dot product, and then we can pretty much add that to the force, that is. So we take the force, or actually what we're going to do here as well, we're going to multiply this with one thing else, and that is the speed. So we take the velocity, we take the length of that, and we're just going to plug that in. So we have a speed as a constant here as well. And yeah, then then we can add it to the force. And then we just plug it into force. Cool. Let's see how that looks. It probably looks like crap right now. It doesn't seem to do that much right now. So let's look. What did we put the multiply constant on though? Put it on 1. Let's bring it up to like 20. See what happens. Just exaggerate things. We're gonna lock here so we can see what's happening. Yeah, we get things here. Maybe it's a bit exaggerated, but let's bring it down to like 10 or something. And it's super big right now, so it's hard to tell, but yeah. Let's do some things here with the box thingy. So I think this should be like super small compared to what it is, like 0.3. Oh, actually, we're gonna change this. We're gonna do a grid instead, because we're gonna displace this, so it's better to do a grid. So let's do a grid, and let's just do 0.3 and 0.7, and good. Let's see what's happening. Now we see it's a little bit better. It's a bit, yeah, it's a lot of pushing thing going on here, but it kind of works. Yeah, get these little twirly tiny things. So what we could do now is we could add in like a regular pop force as well, just to give it a little bit more randomness. So let's do that. Let's bring in something like amplitude 0.5 maybe, swirl size 1 maybe to start off with. Gives us a little bit more randomness. And also I think like, yeah, it's quite decent. We could of course also scatter a little bit more points, bring that up to 20 to see what's going on. Oh, here's the thing, we don't need a grid scale to be like that. We could probably do it down to like 2 by 2. No, actually want 4 by 4 here. So we can do a little bit of things with it, because we need to do the displacement as well. Yeah, so there's like a general problem here that is I think they're not slowing down enough, maybe. So we could bring up, could do two things. We could do the regular pop drag, which is there. We can bring it up to 20 maybe. So we got the general drag. That's a little bit better, more obvious. And also, let's see here. I think the spin is too little here. So let's bring up the pop torque. I'm going to do multiply by spin amplitude instead here, and see if we can get up it to maybe 2. I don't know if that's better. Yeah, that is better. Yeah, now we have a little bit more spin to most of them. Yeah, I think I'm gonna do the push upwards. Gonna increase that a little bit. Let's see what we should bring that up to. Maybe bring it up to 30 instead. Let's see how that looks. Yeah, it depends on what look you want, of course, but that's pretty good. And yeah, I'm gonna the push side things I'm gonna bring up as well a little bit. I'm gonna multiply that. I don't see any problem with exaggerating it. We could also look at the dot ramp here and maybe do like something like this, maybe something like that. I don't know. Let's see what's going on. Yeah, we have the general motion is there, which is important, and yeah, it's starting to look good, I think. Yeah, we get nice kind of people that dudes that get stuck in there. Good. So yeah, I think we're kind of happy with this at the moment. Let's move on to the grid, because the thing we did is, well, on here is to have it deformed as well in the air, and that's pretty simple actually. So what we do is just put on a group here, and let's just move into this thing. So what we want here is very basic thing to, we just want to take some points here, and we want to take the outer points here, these, and we want to take these points, and then we group them, and then we do an attribute triangle where we just deform them. But first we're going to give them the rest position as well. So let's just do v at prim rest equals to at p. That's very basic. We just have the position of them, the original position, which is good. Yeah, and then we have this thing here. So now we can move on to, sorry, so big. I don't want to see the points. Please, can I not see the points? Good, thank you. We could also remove, sorry, we're just going to remove the CD visualization here. I shouldn't have it. Let's remove this. Good, so there we go. And we can just re-sim it and look at it. Yes, it looks good. So what we're going to do now is we're going to look at the displace thing. We could also, actually, I also want to do another thing. I want to give them ID, and that's also pretty simple. We can just do, because we have an ID from the points, but we want, if we want ID for every point here, if we want to do something random with them, I don't know if we want that. But let's do it, and we do a second ID as well. So we do I at ID 2, and that's equal to our ID, which is for the points then. We can subtract by 1, so we start at 0. And then we can basically just do it by 16, because we have 16 points, and we do plus I at prim ID. Did we give them a prime ID here? No, we didn't. Sorry, we're gonna of course also give them a prime ID up here. I forgot that. So let's do that. I at prim ID equals to at ptnum. I don't know why I want that ID for everyone, but we do some things here to just prepare it for render. So if we look now, we look at ID2 here. We have a unique ID for everyone, but maybe we should not subtract 1 from the ID then. So just start at 0. Yeah. So here we have an ID for every point as well. It could be good to have. And they're calculated from the, if we just do ptnum, it will change when we have changing point numbers, so it's better to do like this. And we can also do like an, we could also put an UV project up here, so we have that if we want to do UVs for it. Yes. Oh, fuck me. Sorry. I know I'm doing this in a kind of annoying way right now, but we could just, I just realized things that we want. We can just look at the quick shade here, just to see that we have UVs on it. So that's good. Good. So yeah, let's move on to the, I don't get why it gives me these things all the time. So let's move on to the displacement. We can call this give ID. And we do another attribute wrangle, and we call this displace. So basically what we're going to do is we're going to, when it's moving towards our axis, the up axis that we used, we want them to be displaced based on their speed. So it's not that hard, but we need some floats. We need to do a float which you call displace or disp. We also want the absolute dot product, so we can do that. Abs dot equals to absolute dot. We also want the up. We need to. Sorry, we're also gonna bind one thing here. Sorry, I can move back a little bit. I just realized things. We're also gonna bind this as a vector instead, so we have it. So we don't need to do the thing. We're just gonna call it up direction. So we have that binded as free floats. Sorry, just realized things while we move on. So yeah, so we're gonna do vector up. Let's do like this instead. We could just use it, but I want to be sure it's normalized. It should be normalized, but you can never be too sure. So we just do v at up direction. That's good. And we also want the down direction actually. So we do v vector down equals to 0 minus up, which is good to have. Down, not down, down. Yeah, and then we want the normalized velocity. So we do that as well. We do a vector normalized velocity, which equals to normalized velocity. V at v. And then we want the up distance, which is the distance between the up vector and the normalized velocity. So let's do that. Let's just do a float up dist, and we're gonna check what's furthest. We know if it's pointing upwards or downwards. So we do distance up and nv, and then we can just copy this and we do down distance, and this way we know if it's further down or up, if it's, and that's pretty handy to have. And then we just do something if in parentheses up dist is greater than down dist. Then we do something that is displace, and then we want the down distance, because whatever shortest is the way it's facing. So then we do down displace is equal to down dist. and else it should be displays equals to, then we need minus for the up distance because it's negative. Good. There we have a little bit of code. And then we want to displace direction. What way are we displacing them? So we do vector displace direction, and that is equal to our up direction, which we stored later before. And we can just do that by multiply that by the displace, which we calculated, and it should be negative or positive depending on what direction we are. And we can just multiply that by absolute abs dot, or did we do that in, we did something like that, I guess. Abs dot. Good. So now we have the thing here, and we also want to calculate the speed actually. So we do float speed equals to length, because we want the speed to be a variable here that gives us the amount. And then we can just at position equals plus equals to displace direction multiplied by a channel float, which we call amount, and we can multiply that by speed. And then we want this to just run over our group. And if we now do like this and we bring this in, you see we get them displaced in the direction we want. And this we probably want super low, maybe like, I don't know, 0.2 maybe. And let's look at this. As you see now, they bend nicely when they turn, and it's based on the speed and the direction and everything. So yeah, that's pretty much it. We could also, of course, we can make to take things a little bit further here. We could also give them the real rest position here. So we put on another angle, which we call rest. And this is, I mean, this won't be shown here. This is more when you render. So we call this rest 2 maybe. And then it's just be v at p&t rest plus v at prim rest. I think they call like that, right? I'm just gonna see here that we have dot rest, point rest, prim rest, prim rest. Okay, we have two. Okay, sorry. So it's prim rest, like that. Should, of course. And then the rest 2 is correct. Yeah, that's good. And we see it's different from each. No, it's not. Prim rest. It is not. V at prim rest, V at point rest. Yeah, it's different, sorry. I just missed the fact that we didn't change in all directions, but it changed. Yeah, so that's good. It's different for everyone. Cool. And what we could do now as well, I don't want to see it like that. The good thing here is we can actually, if we wanted, it doesn't really matter because it won't do that much, but we could also trail this now and compute velocity, so we get this small little movements from, so we have a little bit difference when it won't show if it doesn't come super close, but it could be cool to have. And yeah, then we can subdivide it, and that will work as well. We will get a little bit nicer, as you can see. You can do a depth of 2 here. No, we don't need a depth of 2. That's extremely accelerated. We do 1. We could probably just do point normals, and that would probably give us pretty much the same result. And if you want, you can extrude it as well, of course. You can put down normals here. And then, yeah, it's super fast. And if you want it faster, you could also do out of frustum thing, but which I did for mine, but that's really not the point here. So yeah, let's just play blast this and see what we get. Okay, we're looking at it from, you know, where it starts, which is maybe not what we should. Let's just abort this, sorry. Let's look at a bit further down and we do this to 500 instead. So let's see what happens here. Oh, we should not look at it as subdivided. We should just do like this. Boink, and there we have it all. We don't need to look at it subdivided. But yeah, it's definitely working and as intended. And we got this kind of neat, swirly kind of motion to it. Kind of basic, something a little bit more complex, but if you just break it down for yourself, and I think you will understand it. If you don't, probably you do. It's just me that feels something so complex because I'm stupid, but yeah. So that's it. Yeah, thank you. Bye.